Okay. Now these things look pretty similar in some ways to Green's theorem. And they follow from Green's theorem. They're just three-dimensional generalizations of Green's theorem. One for flux, one for the flux of the normal component, one for the integral around a curve. So, I actually checked your book's notation before I came in. I like to use dr. Sometimes I'll use ds, but I'll stick with dr. It means the same thing. Okay? And this is over the region, and this is over a closed curve bounding the region. Okay? Now there are restrictions if the function doesn't behave right within the region, or even maybe on the surface, on the boundary of the region, then it doesn't apply. Okay, and if the region isn't simply connected, you gotta be careful about that, okay? So this is pretty much just saying that, well, you got a small region here, and the picture we had before of a circulating field that gives you a curl, okay? It makes sense that the bigger the region, if this is a tiny region, then it's really easy to show that the integral of the curl around the boundary, the integral of f around the boundary is equal to the curl at the center with just a trivial discrepancy, okay? So it makes a certain amount of sense that if the region gets bigger, you got more curl inside of it, and of course you got a bigger boundary, right? So if you multiply the curl by the area, it sort of makes sense. What you get ought to be related, ought to get bigger as the integral around the boundary gets bigger. Now there's a problem with that because the area increases as the square of the length of the boundary. Okay, so there's more to it than that. And so what I'm saying is just, that's a very intuitive idea, but it doesn't quite work out, but we'll work out the details. And it really just comes down to you take a region and you break it into a bunch of rectangles. Show that it's true in small rectangles so that, you know, the curl being a vector normal to the surface, or, well, it's a vector, okay? And you got your normal to the surface and all that stuff. But, you know, the circulations around these boundaries cancel out except for on the outer boundary, just like what we saw when we looked at a proof of Green's theorem, okay? So we're going to get to that, but there's the kind of the picture. You integrate the curl within the region, and you're integrating the component of the curl that's perpendicular to the region.
What is ds?
The surface area, but it's oriented surface area. We've got to talk about orientation too, okay? So it's just your delta S increment, but with a normal vector, which you get from your TU cross TV. So what you're going to end up with is, this is just going to be TU cross TV without the absolute value. So it gives you a vector normal to the surface with the same magnitude as the ds that you would use if you're integrating a scalar. okay? And then you dot the curl with that. So it's very simple. Everything you're doing on surface integrals with parameterizations, everything you did with that question you asked me, you just take off the absolute values in the 2u cross 2v, and now you got something to dot with the curl. Okay? So that becomes pretty simple. And your book actually does a proof of Stokes' theorem in the situation where your surface is a region bounded by the graph of a function f of x, y, two variables. Okay? And I think the region you're looking at is just a region within the xy plane. So you got this surface bounded by the xy plane, bounded by a region in the xy plane, and then whatever else you have. So yeah, we'll talk about that, but that's what it looks like. And you see that the mechanics of doing the integral are really no different than what you've done. You just remove those absolute value signs and you've got it, okay? And this is just another line integral, okay? So that's Stokes' theorem. In the divergence theorem, I'm using a capital V. Yep, no. I'm not sure of the letters your book uses, but yeah, this is a region, a bounded region in three-dimensional space. And this is the surface of that region, a closed surface. Okay? So F is a closed surface, S is a closed surface, bounding region R. Okay? And this is the integral of the normal component of the force of the field.
The N is?
Yeah.
Or F dot N?
F dot N, that's just, N is normal to the surface, and F is your field, whatever direction it has. You take the component of the field in the direction of the normal, and that's what you're integrating. Okay? So if you think like of a fluid flow, if this is the fluid velocity, if F is your fluid velocity, it tells you at what rate fluid is flowing across the surface at any point. Okay? You integrate that over the whole surface, you get the net flow across the surface. Okay? Now the surface bounds the region. Okay? And this says that you have a divergence. If you have a divergence within that region, then you integrate that divergence, and it's equal to the total amount of flow across the surface. And in particular, if you have an incompressible fluid, well, what goes in has to come out. There's no compression or expansion, okay? Which means that the divergence is everywhere zero, so that this integral has to be zero. Now it also applies to electromagnetic fields. And I'm going to pull a little equipment off the shelf and at least show you a couple of things about the way electric and magnetic fields interact. Even though we haven't really studied it, there's some very concrete things that actually lead us directly to Maxwell's equations if we generalize them with the stuff that you're learning here. Now, solving Maxwell's equations, they're partial differential equations, and they're difficult to solve in most cases, okay? But these,
Are those his equations of electromagnetism?
yeah, they generalize electromagnetism. They give you a complete package for electromagnetism, okay? They were generalized by James Clerk Maxwell back in the 1860-ish. I don't remember, there's a lot going on there, Civil War and stuff. I kind of mix up my memories of those days. Okay. So I forget when he wrote me that letter saying, "Hey Dave, does this look pretty good?" I looked at it and said, "Jimmy, I think you got it." He didn't like being called Jimmy, but you got to keep him in his place. Okay. That poor guy died pretty young. I think he was 47 or something like that. I felt bad about that. I don't think I had anything to do with it. He was over there in Europe. Okay? Makes sense? Okay.